Hi everyone. Today we'll be talking about how you can build neural networks in different ways using various frameworks. So let me share my screen and get it started. Okay, so the code for everything I'm going to show will be present in this repo. It is basic neural networks. So now let's start with the first thing, that is NumPy, implementing a neural network using NumPy. So there are three main steps in building a neural network. First is forward propagation. Then you have back propagation where you're updating the weights, and then there is the where you're calculating the gradient, and the third is updating the weights where you use the gradient to update the weights. So now let's take a look at each step one by one. So first we can create a synthetic data. We are going to be generating a non-linear synthetic data. That would mean that our data would be cubic in nature. So we have three weights as true weights. This will help us generate a data, and our actual value will be x cube times weight true. So whatever is the value times cube this, then x square times 3, and then x, that is 1 into, and then bias. So this is what a true data looks like. This is a visualization of four-dimension data, where the fourth dimension is basically a gradient to represent the value, where each color represents different values. Now let's look at the first problem, that is forward propagation. So in forward propagation, what you'll be doing is you'll be taking your input, multiplying it by the weights, and generating the output. So first, we just figure out some how to do certain matrix multiplication. And now a neural network will be made of multiple layers. So we'll divide it into classes. So we'll have a linear layer which will handle the weights and input multiplication. Then you have the ReLU layer which will handle the application of ReLU. And then you have the main neural network class. The neural network class is basically going to club everything together. So firstly, we define a layer, which is a linear layer, a ReLU layer, and another linear layer. This will be our output layer, and we give it the dimensions. Input dimension will be the dimensions of our input. So in our case, the dimension is 3D, so it will be 3. Hidden dimension is basically number of neurons in each layer, and output dimension will be your final output, how many neurons you want in the final output. And next, first we build a model. We just make sure that the shape of prediction and true and the actual true is true. Here, so far, just to try out if we can get the forward propagation and back propagation working, we are only going to be working with two layers because once we have that thing working, we can increase the number of layers as we want. Now, so we make the forward propagation, we visualize how the distribution looks. And now, once we have done the forward propagation, we want to calculate the cost between the true and the pred. So since we are working with a regression problem, for this purpose, we'll be using the cost function of mean squared errors. So we'll be creating a separate class for mean squared errors. And now it is the time we'll start integrating back propagation as well. So mean squared error is basically y minus y cap the whole square. Now if you y true minus y pred minus y true the whole square divided by size. Now the question over here is what will be the backward? The derivative of it will be 2 times the difference divided by y true. The same here, the only difference is at the end of our forward prop, we can also be able to call the loss to compute the loss. We can see the loss is kind of high. Now let's look at back propagation. So for as we did it for mean MSE loss, for each of the function, we'll calculate the gradient. That is for backward propagation for ReLU, whatever is the output gradient into ReLU is basically x when x is greater than 0 or else it is 0. And same with linear layer, which is WXT. So with respect to WX plus P, and so with respect to X, the gradient will be W plus P W, and with respect to W, the gradient will be X, and with respect to B, the gradient will be 1. So this is how we set up the gradient, and we set up the update function, which is just going to take the gradient weight and update the existing weight using the formula new weight is equals to old weight minus 1 minus the learning rate into the graduate. We define our neural network in this fashion. So now we got things working. We will be needing three layers. So linear layer, ReLU, linear layer, ReLU, and the final linear layer. We set up the loss function for the neural network, which will be mean squared loss. We set up the back propagation, which will we set up the logic for back propagation. So for each layer in the reverse order of the list, that would be from the last layer and so on. We'll calculate the gradient, then update the gradient, and then we define a fit function. The fit function is basically gonna, for the number of epochs we describe, it's just gonna keep on updating the weights. So, and then we instantiate our neural network, our loss function, and fit the model for 100 epochs. And you can see slowly and gradually the loss is decreasing. And once we can visualize the predicted data and the underlying function, we can also visualize the loss over each epoch. We can see we started with really high loss and slowly and gradually the loss decreased. This is how you can implement a basic non-linear regression neural network using nothing but NumPy. Now we have other features that can help us. What do you call it? We have other frameworks and the features which they provide, which we can use to help us make the process better. Let's look into that. The first thing we'll be looking into is PyTorch. So instead of using NumPy arrays, we'll be using tensors. Now initial steps remain the same, which is we describe the true weights, the true bias, and generate the synthetic data. And then firstly, we implement everything from scratch. So now it is same as what we did for NumPy. The final output of my NumPy is the same as what we did over there. But instead of using NumPy over here, we are using PyTorch for tensor calculation. So you don't see NP anywhere. It's pretty much the same thing where you have for each class, you have the forward propagation, the backward propagation, the update method, the call method, and so on. So you build a three-layer neural network similar to as what we did. It is exactly same as what we did so far. Instead of NumPy, we are just using Torch tensors. And then you fit the model for 10 epochs, you see the underlying distribution, the loss, and now comes the interesting part. So the tensors in PyTorch has a gradient feature which basically tracks all the gradients that have been, all the operations that has been applied to a tensor, and it allows you to easily compute the gradient for each operation. So if we do that, then so we can use that feature to our advantage, and that helps us to reduce the computation, we reduce the code which we needed to write for backpropagation. So here we define our layer. We just define the forward operation for the linear layer. Similarly, the forward operation for the ReLU layer. We define the neural network as combination of three layers. We define the overall forward propagation, the loss, and this is where things gets interesting. So when I say torch.nograd, basically we won't be tracking any gradient at this point, because this block of code is just going to be used for updating the grades. So when we calculate loss, at this point we applied all the operations. The grad feature, the gradient feature of the tensor is going to track all the operations, and it is going to help us generate the gradient, generate the difference of so basically, dou L by dou W. It's going to help us generate that, and we use that for updating all the weights and biases. And after that, we set the bias for each layer to 0 because we don't want the previous iteration's gradient to affect the next iteration. And then again, we perform the training for 100 epochs. We can see the predicted function and the underlying function. We can also see how the loss has decreased over the epochs. The next is right now we are performing simple weight updation. However, we can use an optimizer to help us reduce the load and make the weight updation more operational. And at the same time, we can also inherit the NN modules present in PyTorch to further reduce the line of codes which we have. So over here we just define a linear layer. All the classes which we have built so far are now going to inherit the NN module. So it allows us to include some more functionalities and reduce the line of code required. And then again, we describe the forward function, the backward function, the update function, the fit and loss, and then you build. And then we fit the model. The superclass O everywhere is just calling the constructor of the NN module. Yeah, and this will allow us to get metadata of the model, such as the number of trainable parameters and everything, without having to actually specify that in the code. This is the same thing we are doing, but this time with the train test split. And now using PyTorch and builds functionality. So this time we are going to be looking at a classification problem. We basically create a by built-in functionalities. I'm talking about layers. So still now we have been defining the way a layer works by itself. However, some popular layers such as linear layer, dropout layer, CNN layer, you have a ready-made implementation for them in PyTorch. So in this example, we'll be just looking at how we can use those implementation. First, we create a data set. Now we are going to be using the sequential API. The sequential API just basically lets, okay, we have the first layer as a loop with input as 3 and output as 10, then activation, then linear, then again linear, then sigmoid activation on top of it. This time, instead of building our own loss function, we'll be using the binary cross entropy loss function. We'll be using the Adam optimizer, setting the learning rate over there. And then we go through the same training loop. We also understand we are performing sort of batch operation instead of using the entire data to update the weights. And when we go by batch, at the end of each batch, we update the weights. You can see after 100 epochs, the losses or loss on training set is extremely low, next close to zero, and the accuracy on the training set is zero. So everything has been taken care of by the training loop. Then we just want to use it to make predictions. So we just follow this in the test split. We want to make sure that the operation doesn't affect the gradient. So that's why we have a no grad. So don't track any gradients. And then we track the output on the test set. We can also see how the loss and accuracy has changed over the epochs. And now this so far we use the sequential layer, which is just defining all the layer in the sequence. Now, what if we don't want to do that? We want more control. In that case, we can use the existing layers without using the sequential API. We can use the layer functionalities without using the sequential API. And this is what we'll have to do. Basically, define a class where each instance variable is one of the layers, define the hover propagation, and that's it. Since it is already implementing the NN.module function and you're using the layer function, the backpropagation and the updation method is already defined over there, so you don't have to worry about it. You specify the loss function which you want to use, you specify the optimizer, and then you just run the training loop again, and it is going to be able to do the same thing. Now coming to PyTorch Lightning. PyTorch Lightning is basically another version of abstraction on top of PyTorch, which allows you to keep your neural network code in a much more organized manner and lets you add more functionalities to it. So first thing you're going to do is the code is roughly going to look pretty much the same. So we build the synthetic data, and this is where things get interesting. We create our model, and instead of implementing NN.module, which we were doing earlier, we implement the Lightning module from PyTorch. And then we need to implement certain functions. So you have your forward propagation, you have the training step. So for a number of steps, you're going to run this. Then you have the validation step, what you want to do in the validation step on train epoch end. So once a training epoch end, what you want to do on validation epoch end. So once validation for each epoch ends, what you want to do. Then you have configure optimizer, basically which optimizer you want to be using. And then we just have a train set. We use a tensor data set object to generate a train set and the test set. And then we fit the model. After filling the model, we can easily visualize how the training and the validation loss has changed over each epoch. And we can see how the predicted value distribution is different from is similar to the underlying function distribution, showing that a neural network has been able to map the underlying function quite effectively. Now coming to TensorFlow. So just like PyTorch, TensorFlow works with tensors. I'll be showing you different ways of building neural networks using TensorFlow. So firstly, we just define the data, the true data, visualize how the data looks. We do a train test split. And then now first thing is everything from scratch. So this is similar to what we did for NumPy and what we did for PyTorch. Basically, each class will have a forward propagation, a backward propagation, and an update method. In this case, we have performed an, yeah. So forward, backward, update. So you first you go forward, then you for all the layers present in this dictionary, in this list, in the reverse order, you calculate the gradients, update the weights, and so on. And you can fit the model, track the epoch, underlying distribution. Now the interesting part, just like how TensorFlow allows, how PyTorch allowed us to track gradients of all the operations that have been performed on a tensor. Similar thing is possible in TensorFlow, but the feature is called different. In PyTorch, it is called auto-differential, whereas in TensorFlow, it is called gradient tape. So when using gradient tape, we don't have to worry about implementing the backpropagation method for each of the classes. So you have our model, which is basically weight bias. We have three layers, so three sets of weights and biases. The call method uses the first set of weight bias, applies ReLU, second set of weight bias, applies ReLU, and then the third set of weight bias, where you do not apply the activation function over there. You define the loss function to be mean squared error in this case, and now you set up a gradient tape to track the operations and then use that to calculate the gradient. You calculate the gradients for each operation and use that to change the weights at each layer. This is the part that is interesting. This is what the gradient tapes allows us to do. So we do not have to write the back propagation for any of it. And now train variable and validate. These are the additional steps which I added. Just tracking the loss, train and validation loss at each stage. Underlying function. Now we'll be using low-level APIs. So this would be subclassing a class. So how we did an in dot module in PyTorch, we will be using tf dot module. These are module and these are layer and model abstractions provided by TensorFlow, and we'll be using optimizer instead of normal weight updation. You are pretty much doing the same. You have the call method, which is basically your forward propagation. You define a loss, you define the validation function, you define the train function, and then you train the model. The main thing is your class is inheriting the TF module class, and that enables us to have additional functionalities to the model and allows us to write fewer lines of code. Once you train the model, you can plot the train and the validation loss, the overall performance, the underlying distribution, and the predicted distribution. The next way is using built-in layers. So far, we have been writing the code for linear layer or the dense layer as it is called in TensorFlow by itself. However, TensorFlow, just like PyTorch, TensorFlow also has very some popular layers written in them, such as a dense layer, dropout layer, convolution layer, and so on. The main difference over here is in TensorFlow, the activation function is not a second layer by itself. Rather, it is added as part of at the end of a first layer. So in the first layer, we are specifying it to be dense layer. We are giving it the input and the output dimensions, and we are saying that we need to apply an activation function ReLU on it. And then the call is basically using a forward propagation on it. Then we specify the optimizer we are going to be used, the loss which we are going to be used, and then we compile it. So model compiling is basically nothing but connecting the optimizer and the loss function with the model which we created. And to enable your model to have compile and functionalities, you have to make sure that it implements the tf-keras.model parent class, so that you don't have to worry about the code for implementation of fit and compile. You fit the model you have, and then you can plot the train loss, validation loss, use it for making predictions, and so on. Now, TensorFlow also has functional API, which allows us to write code, build a neural network without writing any classes or worrying about inheritance or so on. So what you can do is you can have the first thing is we have our input layer. The input layer will have shape this, and from that we give it to, we want the data to go to the dense layer, the first dense layer. First dense layer has a set of weights and an activation function ReLU. Now we want to apply this waits and activation function ReLU on our input layer. So this by itself is going to return our function to us. And this is the second part of this is the calling of it. This is how we are going to call that function which is returned by the first part. So that's why it's called the functional API. And so this returns the output at 2. And then for the third part, we need to give the output at 2 as its input. And that's how you get the final output. Again, you'll compile the model, attach the optimizer and the loss function, fit the model, and then you can use the model history. This is so over here we did not implement the logic for tracking the history, but rather TensorFlow does it for us. And we can track the validation loss, the train loss, use the model for making predictions, and so on. Now using the sequential API. So sequential API is similar to functional API, but only much more simpler. It is similar to the sequential API which we saw in PyTorch, where it allows us to define a more. So this part I'm showing you using MNIST data, but basically what it allows you to do is just specify your model in a particular manner. So instead of having a class where you have each layer and you have to write the you have to manually write the backpropagation. All you do is you specify the layers in the order which you want the data to pass, and then TensorFlow will take care of this. So since MNIST data is an image data, this is a 2 by 2, a 2D data set. The first thing we'll do is we'll flatten the data. So that is the flatten input. After that, you have a couple of dense layers and the final softmax layer with 10 neurons because it's a 10 class classification problem. You compile the model, you fit the model, and this is how you build a neural network using sequential API. Now the last part using JAX. JAX is basically a new library which is highly used in building transformers and so on, but we'll be using it for building basic neural networks. So first thing first is we define our data set. We split the data set into train and test, and then you have to implement a certain type of parameters. So first you define the set of parameters, which is W1, B1, W2, B2, W3, B3. You define a ReLU function, which is going to apply ReLU operation to whatever input it gets. You define a forward propagation function, which gets the parameters and applies ReLU and is similar to what you have done so far. And then you need to calculate loss, and then you have the main function update. So this is where the training actually happens, which is you'll get the parameters, you'll get the prediction, and then we manually do backpropagation using chain rule for each of the variables that would be a W1, W2, W3, W4, W1, W2, W3, B1, B2, B3. We manually perform backpropagation and update the weights. We basically set a seed value so that every time we run it, the weights are same. Because in the first iteration, the weights are generated randomly, and then we can fit the model and we can fit the model. The similar plots we've been seeing so far, which is the loss over epoch and also the underlying function and the predicted function. And now we'll be using low level API. So the main thing which low level API which we'll be using is the grad from JAX, the grad API from JAX. So this API is going to help us reduce the lines of code we need to write for updating our weights. So basically, it's going to help us reduce the lines needed for backpropagation. The rest of the codes remain the same initialization parameter, the ReLU, forward, MSE update, MSE loss. Here, where you can see the update over here is now much smaller than the block of code we had earlier. Now, all we are doing is we are calculating the gradients of all the parameters X and Y with respect to MSE loss, and then we use the value from there to update the weights. And then we call the function for 10 epochs. This is the training part, and we have the model trained. And after that, we can use the forward propagation method to get the prediction, perform some plots, and so on. Next is high level API. So high level API will be using Flax. Basically, we'll be implementing decorators for an N compact and jax.jit. What this will allow us to do is we can, instead of having writing W1, W2, and so on, we can directly use a layer-like functionality, what we saw in PyTorch and TensorFlow, to define the model and the forward propagation. Then create a train state which will state the model which will initialize this model and give it weights. So you can think of a state as a, so as we go through each epoch, at each epoch the weight gets updated. Now the instance of a model at epoch 1 will be one state. The instance of the model at epoch 2 will be state 2. So you can think of state in that manner. So the train state will basically just whatever parameters are set for the weights, that is your state, you initialize an optimizer, and then you apply the model.apply function to it. Model.apply is nothing but a JAX version of training. And then you define a train step function by implementing the JAX.decorator. So state, as I said, is nothing but the model at a particular point, and batch is nothing but the batch of data on which you want to perform. So on your model, you are applying the parameters. The parameters are basically what you'll get from the state. The parameters are your values of weight. So you'll get it from the state. You apply that to the batch function. You'll get the logits. The logit is nothing but your Y prediction value. And then you use it to calculate MSEJ. So this is just basically a formula for MSE. And in the end, you return the state and the loss. The state is basic. Now, what the state which you are returning is the updated state. That is the updated weights. This is the line which shows you where the weights are getting updated. And then we define the predict function just so that we can, test the data on the test set. Again, we have a key. We set up the input and the output shapes, and then we perform. We run the train step about 10 times, and then we can visualize the results. So this is JAX using high level. So you can, if you feel free to go through the repository in depth to get a better look at what each and every line of code is doing. But this is at a high level how you can build neural networks using various methods and various frameworks such as PyTorch, PyTorch Lightning, TensorFlow, JAX, and NumPy. Thank you.